Good morning. Welcome back to Index Properties of Soil. The last class we discussed about determination of water content by oven dry method. Now let us understand how to determine water content by using the other secondary methods. The next method of determining water content is Pycnometer Method. As we already discussed, of the various methods available, it is the oven drying method is the most simple method, easy and most reliable method. Hence, it is used for all practical purposes in practice. In the absence of oven drying method, means if it is not possible to perform determination of water content by oven dry method, then we go for the next alternative methods. The next method is the Pycnometer method. Pycnometer method of determining moisture content or water content is an approximate method. It is ideally suitable for cohesion-less soil. Here the procedure to determine water content is almost same as that of determination of specific gravity of soil, except that here we use the wet soil for all the observations along with the specific gravity of soil. Means in Pycnometer method of determination of specific gravity, there we use dry soil passing 4.75 mm air sieve, whereas to determine water content of the same soil, we use the wet soil as it is, and to determine water content we need the specific gravity. So observations are, it is W1 is the weight of the empty pycnometer, W2 is the weight of pycnometer and wet soil approximately at a height of 1/3 of the pycnometer height. Then W3 is the weight of pycnometer plus soil plus water up to the top of the pycnometer. Here again to make sure that it is all the entrapped air should be removed. Lastly, W4 is the weight of pycnometer plus water. So with these four observations, we can calculate a specific gravity or water content of that soil, that is equal to W2 minus W1 that divided by W3 minus W4 into G minus 1 divided by G minus 1. So by using this relation, we can find out specific gravity of water content of soil quickly. Again, it is an approximate method and it is ideally suitable for cohesion-less soil, means it is suitable for coarse grained soils. The next method of determination of water content is sand bath method. Sand bath method of determination of water content is a field method. Wherever this facility for drying soil using oven is not available, or wherever this electrical connection is not there for oven, under such circumstance we use this method. This method involves drying of the wet soil placed in a pan or a pan on a flame. Flame may be created by means of a kerosene stove or gas stove. So by using simple procedure, Again it is whatever the container or a can which we use, that W1 is the empty weight, W2 is the wet weight plus the can or container, and W3 is the dry weight after drying of soil. So with these three observations we can comfortably calculate the water content by using the relation W is equal to W2 minus W3 divided by W3 minus W1 multiplied by 100, that is weight of water divided by weight of dry soil multiplied by 100. And of course this determination of water content can be made quickly within fraction of minutes, as it is there is a regulation in the flame of a kerosene stove, or in case of a gas stove. Again it is an approximate method. The third method or fourth method of determination of water content is rapid moisturometer. Here to determine moisture content we use a suitable chemical. This method is based on the principle that the chemical added to moist soil will liberate the gas. The amount of gas liberated is equal to the amount of water present in the soil. The most commonly using chemical to determine the moisture content here is calcium carbide. Rapid moisturometer is a portable equipment. It resembles like our thermoflask which we use for maintaining temperature of the water or the tea, coffee, milk and all for a larger duration of time. For the soil, water content is to be required to be placed in the rapid moisturometer, and required amount of required quantity of calcium carbide is to be placed inside the rapid moisturometer, and it is to be vigorously shaken. So when calcium carbide is added to soil, wet soil, so moisture content present in the soil react with the calcium carbide, liberating the acetylene gas. The amount of acetylene gas liberated or released depends upon the amount of water present in the soil. Again it is a quick method. So even it is possible to find out the moisture content of soil by using this method within a minute. Within a minute we can determine the moisture content. Again it is an approximate method. The last method of determination of moisture content is torsion balance moisture method. Torsion balance moisturometer, again it is a portable equipment connected to electrical supply. Here infrared ray of heat radiation is made to penetrate into the wet soil. As a result, quick heating of soil take place by removing the water present in soil. Then, knowing the original weight of the wet soil and the dry weight of the soil, we can easily find out the weight of water present in the soil. And anyway we dry soil till all water content gets evaporated. So knowing dry soil weight and water content, we can quickly calculate moisture content by using the equation W is equal to W2 minus W3 divided by W3 minus W1. So again here water content, weight of water divided by weight of dry soil, that multiplied by 100 gives you the water content. So like this we can determine moisture content by using these 5 methods, namely Own dry method, Pycnometer method, sand bath method, rapid moisturometer method, torsion balance method. Of all these methods, it is the Own dry method is most easy, simple and most accurate, and it is applicable for all practical purposes. So, this is about moisture content. Next, let us understand or learn about the next index property. The first index property is color, the second index property is shape of the particles, the third index property is grain specific gravity, fourth index property is the water content or moisture content, then the fifth index property is in situ density. Let us understand this the heading first, in situ density. The term density we use alternatively to unit weight. Unit weight or density, the terms which we use alternatively in order to understand the closeness of the particles, closeness or the denseness or looseness of the soil particles. In situ density, in situ means inside, the density is the thing, but the relative closeness of the soil. Always we find soil in the site, always soil is available in the site. Site means it is always available outside the office. Outside the office it may be site. Site may be very close to the office or laboratory. Site may be far away from the laboratory. We call the site. Site means it is the where which we are going to propose the construction activity. Construction activity means for any structure. Before taking of construction of any structure, it is customary and mandatory to know the soil properties of soil, to decide the foundation, type and extent of foundation. The first and foremost test to be conducted when we visit to the site, proposed site, is in situ density. Again, that is in situ, in the site, knowing the denseness of the soil. What is the use of this in situ density? The purpose of conducting or determining in situ density is know the denseness or looseness of the soil. Where do we conduct this in situ density? This in situ density test we conduct below the ground surface at reasonably hard strata. So, we construct foundation, always we construct the foundation or we lay the foundation always below the ground level. No foundation is laid on the surface, whatever the type of soil strata it is. It may be a loose strata or it may be hard strata. If it is loose strata, it is obvious that we are going to remove that loose soil till we reach the hard strata. If it is a hard strata available even on the ground surface, we chip out that hard strata and place the foundation reasonably below the ground surface. The objective of providing foundation reasonably below the ground surface is to provide the proper embedment for all the foundations. That is a true practice always. In situ density of soil can be determined in the field by using two methods, namely a core cutter method and sand replacement method. Both are simple methods. Depends upon the type of soil we come across in the field, we use this method. The first method is a core cutter method. It is a simple method. Simple method, easy and quick method. Simple method, and it's very easy to conduct the test, and it's a quick method. Quickly we can determine the density. Core cutter is a cylindrical apparatus. Usually we use a stainless steel core cutter having the cutting edge like this. This is a sharp cutting edge and another edge is the blunt edge. The diameter of the core cutter is about 10 centimeter and height of the core cutter is about 12 centimeter. Here in the soil mechanics or geotechnical engineering, always we are interested with the inner dimensions of the instruments, because we place soil inside the apparatus. So to know the volume of that apparatus or equipment, always we are interested with the inner dimensions. So we can measure the diameter of the core cutter, inside diameter, and also we can measure the inner height of the core cutter. Knowing the diameter, inside diameter and height of the core cutter, we can calculate the volume of the soil. So diameter can be measured, the height can be measured. So volume of the core cutter can be calculated by using the relation pi d square by 4 into h. Volume of the core cutter is nothing but volume of the soil to be accommodated in the core cutter. To determine density in the field, before going to field, first after deciding where the field density is required, we make preparations in the laboratory. In the laboratory, we note down the observations, means the diameter of the core cutter and the height of the core cutter. Knowing the height, diameter and height, we calculate the volume of the core cutter. Volume of the core cutter is nothing but volume of the soil to be accommodated in the core cutter. Then we have to note down the weight of the core cutter. Weight of the core cutter, say it is W1, it is weight of the core cutter, empty weight of the core cutter. So these are the laboratory observations. Next, before proceeding to field, we use this is called as a collar or a dolly. In other words, we call this as a helmet to protect the head of the core cutter. Head means it is the blunt edge is called as head and the sharp edge is a cutting edge. So to protect the head of the core cutter, we use this the collar or dolly like this. It will perfectly fit into the top, like perfectly fitting of the helmet. We decide where we have to conduct this test, and we take this to the field. There we place this core cutter. After placing this core cutter at the location, the core cutter is to be driven into the soil by using the suitable rammer. Usually we use the steel rammer of weight about 10 kg. Rammer will be like this. It comprises of the flat weight surface at the bottom and the rod to hold it comfortably. So by using the steel rammer, it has to be, the core cutter has to be driven into the soil till, suppose say this is the ground surface, core cutter to be driven into the soil like this, including this the collar till it goes inside the soil. After driving the core cutter into the soil, the driven core cutter should be removed carefully by using suitable soil remover like this, without touching the core cutter, without disturbing the core cutter. So like this you can remove the soil all round. Then after removing the soil all round the core cutter, so we have to lift the core cutter by inserting our right hand to the bottom, or right hand or left hand to the bottom of the core cutter, and keeping the another hand on the top of the core cutter. Carefully it has to be lifted. Then it has to be brought to the laboratory. In the laboratory, the top and bottom of the core cutter is to be leveled by trimming off the excess soil, if at all, if there is any. If the soil is projected the beyond the edges, cutting edge or the blunt edge, it has to be trimmed off by using the cutting edge or the spatula. Suppose if there are any undulations at the bottom or top because of presence of this lumps or the gravel, and those undulations again to be the filled and it is to be leveled both on top surface. Then it has to be the core cutter surface to be cleaned. Then finally we can note down the empty, that is weight of the core cutter, weight of core cutter plus soil. So initially we have taken observation, diameter and height, and also we have taken weight W1, empty weight of the core cutter. Then after visiting and performing this experiment, we get W2, it is weight of the core cutter plus soil. So volume of core cutter is nothing but volume of soil to be accommodated inside the core cutter, and the weight of the soil accommodated or what of soil inside the core cutter is equal to W is equal to weight of soil, W is equal to W2 minus W1. So knowing weight of the soil and volume of the soil, we can comfortably calculate the field density. Therefore, the field density gamma B can also be called as the field density can also be called as the bulk density. Gamma B is equal to W by V. So many gram per cc if it is the observations are made in the grams. Later this can be converted into the SI system by multiplying this gamma B by 9.81 kilonewton per meter cube. So this is the procedure to determine the field density. After determining the field density, we can also determine the dry density and dry unit weight. Anyway, we conduct this experiment and we remove the soil to remove the core cutter, and then we brought core cutter to the laboratory. In the laboratory again remove the soil from the core cutter. When we reach to the middle portion of the core cutter, take a sample of soil for water content determination. Before taking soil sample for water content determination, you are to keep ready this water content cup or container, noting down the container number, then empty weight of the container W1. Take the appropriate quantity of soil that depends upon coarse grained soil or fine soil, place it in the container, close the cap and note down the weight of container plus soil, that is W2. Next, switch on the oven, maintain a temperature of 105 to 110 degrees centigrade, and keep this the wet soil inside the oven by opening the lid of the water content container, placing that lid again below the cup. So keep it for 24 hours. After 24 hours, we can take out this the dried soil. Note down the weight of the dry soil and cup, that is W3. So using these three observations, we can comfortably determine water content. W is equal to W2 minus W3 divided by W3 minus W1, that is weight of water divided by weight of dry soil, that multiplied by 100. Once we know the water content of the soil, one can easily determine dry density and dry unit weight. Therefore, dry density or dry unit weight gamma D is equal to gamma B divided by 1 plus W. Likewise, we can determine the gamma D for a trial. Generally, for all practical purposes, we conduct this type of experiment in a site 2 times or 3 times side by side. The average of 2 to 3 determinations are treated as the bulk density, field density, incident density or field density or bulk density of that particular site. All these process till this gamma B quickly we can carry out within 30 minutes. Sometimes we can able to complete. So within 30 minutes we can able to find out the bulk density of the soil or field density of the soil. Of course, to determine dry density we have to wait 24 hours. Then the suitability of this method means core cutter method. Core cutter, as we have seen, cutter, it's a cylindrical steel core cutter having a sharp cutting edge and blunt edge. We simply drive this core cutter into the soil by using a suitable weight of rammer. And after driving, again we remove the core cutter. We take out the core cutter along with soil. Means to take out the core cutter along with soil, soil should stay back inside the core cutter. To stay back, soil to stay back inside the core cutter, soil particles should stick with each other. If soil particles does not stick with each other, means particles separates readily, then we cannot get the core cutter along with soil. Only if you remove the core cutter with soil, only we will get back the core cutter, no soil. That is happening in case of coarse soil. Coarse soil means sandy soils are generally called as coarse soil. If you dry this core cutter can be easily driven into a sand. For sand, even without using this rammer, we can drive this core cutter by using our palms like this, or hands. In a single hand, even you can driven. And removal is also easy. You can easily remove. After removal, we don't find any soil inside the core cutter. Means, so it's of no use for sandy soil. Next, we don't know what is there below the soil surface where we want to conduct the field density. If at all, if there is any chances of having the pebbles or gravel below ground surface, if you drive this core cutter, sometimes the presence of pebbles or gravel will resist the movement of core cutter against the driving. Suppose if you forcibly drive this core cutter by imparting extra energy, there is damage to the cutting edge. Damage to the cutting edge to an extent depends upon the energy imparted. If you drive core cutter forcibly, sometimes it is a broken, so the breaking of this cutting edge take place. As a result, we cannot take out the core cutter along with the soil for the full extent as we measured earlier, because initially we measure the diameter and height of the core cutter, we get volume. If the cutting edge is broken, whatever the soil we take out along with core cutter, there is reduction in volume. So if you find out the soil difference, the weight of soil by difference the W2 minus W1, the weight of soil obtained is an apparent one, it is not a true one. At the same time, the core cutter gets damaged. Though soil, it is a fine grained soil and the soil particles are sticking with each other, and if there is presence of this boulder, means core cutter method is suitable for soft cohesive soil or clay soil where we can comfortably drive the core cutter into the soil without much problem and which does not damage the core cutter. At the same time, if you remove the core cutter along with soil, we can easily obtain core cutter with soil to perform the experiment. It is suitable for soft clay soil and it is not suitable for sandy soil and the gravelly or boulder soil. In sandy soil, it is even if it drives comfortably, we cannot obtain the sand, it is of no use. In gravelly soil or boulder soil, it will damage the cutting edge of the core cutter. Hence, it is even if it is possible to perform the experiment and complete, you cannot get back the correct value of the soil removed from the site. This is the limitation of the core cutter. So, it is suitable only for soft and clay soil. Welcome back. The last class we discussed about field density and in detail we discussed about the core cutter method of determining field density, and we concluded that core cutter method of field density is suitable for soft cohesive soil and it is not suitable for sandy soil, and also it is not suitable for boulder deposit or gravelly soil. Usually we use this core cutter method for checking the field density at the basement level, and also we use this in the case of embankments. During the compaction of embankment, we use the core cutter method. The second method of field density is sand replacement method. It is again important method, most accurate when compared to the core cutter method. This method comprises of making the hole in the field where we require field density by collecting the soil removed from the hole and noting down the weight of the soil removed. Then volume of the hole can be determined by means of sand replacement. Knowing the weight of soil removed from the hole and volume of the hole, we can easily determine field density, and hence after determining the water content of the soil, we can determine the dry density of the soil. This method comprises of two parts. The first part is calibration of cylinder. Calibration of cylinder is nothing but determination of density of the sand. The equipment using for determination of field density by using sand replace method is it comprises of a sand pouring cylinder having a conical portion at the bottom, and there is an aperture, we call it as this is, we can close the hole or and open by operating the shutter. This is called as shutter. And this is called as calibration container we use to determine the density of sand. First stage of the calibration can be carried out in the laboratory. First you have to take dry sand, passing 1 millimeter and retaining in 600 micron or 300 micron. So take pure clean dry sand, passing 1 millimeter and retaining in 600 micron, and fill it in the sand pouring cylinder after closing the shutter. So note down the weight of cylinder plus sand, that is the observation. Weight of cylinder plus sand, that is equal to W1 gram. Next, place this sand pouring cylinder with sand on the glass plate, open the shutter, place this sand pouring cylinder with sand on the glass plate or a paper, open the shutter. If we open the shutter, sand will poured onto the glass plate or the paper. Make sure that there is no movement of sand from top. Then close the shutter, carefully lift the cylinder with remaining sand and note down the weight of the cylinder plus remaining sand. Next, weight of cylinder plus remaining sand after pouring into the conical portion. That is equal to W2 gram. Next, our aim is to determine the weight of sand required to fill the conical portion. In turn, if you pour the sand, it will form the heap. That heap means this is a calibration container. And if you place sand pouring cylinder with sand over this calibration container and pour sand, sand will be poured like this, it will fill the calibration container. Even after filling the container, it forms the conical portion. That is the natural phenomena. Any coarse particles, any coarse grained material, if you pour, it forms the heap. Likewise, it forms the heap like this. Here, by using first and second observation, we can find out the weight of sand required to fill the conical portion. Conical portion is nothing but the cylindrical portion made above the horizontal surface. So weight of sand required to fill the conical portion is equal to, that is weight of sand required to fill the conical WC, that is equal to W1 minus W2 grams. So this conical portion, the cylinder is made in such a way that, so amount of sand filled in this conical portion is equal to the heap formed on the calibration container after pouring sand into the cylinder. So WC means weight of the sand required to fill the conical portion can be determined. Next, note down the diameter of the calibration container and height of the calibration container. So knowing the diameter of the calibration container and height of the calibration container, usually we take it is always we take the internal dimension, the internal diameter of the calibration container and the internal height of the calibration container, that gives us the volume of the calibration container. So volume of the calibration container VCC is equal to pi d square divided by 4 into h, where d is the diameter of the internal diameter of the calibration container and h is the height of the calibration container, again inside height. Next, in the first operation we have filled the cylinder with sand, taken W1. The second step is we place the sand pouring cylinder with sand on the glass plate or paper and we operate the shutter to permit the sand to flow on the glass or paper. Then close the shutter. Again note down the cylinder plus remaining sand, that is W2. So numerical difference of W1 and W2 gives us the weight of sand required to fill the conical portion. It is provided. The weight of sand required to fill the conical portion is nothing but weight of the sand above the calibration container in the form of heap. Next, place without refilling again sand poured already on the glass plate or paper, place this cylinder and remaining sand on the calibration container like this. Place the cylinder with remaining sand on the calibration container and operate the shutter. Open the shutter. Permit sand to flow into the calibration container. So after the flow of sand stop, then close the shutter. Again note down the weight of cylinder plus remaining sand. Next, weight of cylinder plus remaining sand after pouring into calibration container. That is equal to W3 gram. Now, all these exercises is to find out the density of sand. So, with these three observations along with this volume of the calibration container, we can easily determine density of sand. Next, weight of sand required to fill the calibration container horizontally that is WCC, that is equal to. So this is the first operation. Second operation, we are pouring cylinder into the conical portion. Then again the third operation, without replacing the sand poured to the conical portion, we are taking the weight of the sand after pouring into the calibration container. Now obviously W2 is greater than W3. So the numerical difference of W2 minus W3 gives us the numerical difference of W2 minus W3 gives us the weight of sand required to fill the calibration container in the form of heap like this. So this is the sand without the calibration container. Now weight of sand required to fill the calibration container horizontally is equal to, so W2 minus W3 gives us the weight of sand required like this. So minus this weight of sand required to fill the conical portion gives us the weight of sand required to fill the calibration container horizontally. Knowing the weight of sand required to fill the calibration container horizontally and their volume, which is calculated by observing the dimension, inner dimension, diameter and height, we can easily determine density of sand. Next, density of sand gamma S we can call is equal to WCC divided by VCC, where WCC is the weight of sand required, WCC, weight of sand required to fill the calibration container, WCC is equal to W2 minus W3 minus WC. So, WCC means weight of the sand required to fill the calibration container horizontally divided by volume of the calibration container gives us so many gram per cc. So, the average of the 2 or 3 of these operations will gives us the density of the sand in the laboratory. I forgot to tell that we use the sand, dry sand passing 1 millimeter ISC and retaining in 600 micron or 300 micron sieve. So, we know the particle size range, it ranges between, it is 80 millimeter, even smaller than 1 micron. So, the small range sand we use, small range of 1 millimeter to 600 micron or 300, it is a small range, means it resembles the uniform size of the particle. When uniform size particles of sands are used, sands will easily slide with each other and it can easily flow through this small hole. Through this hole sand can easily flow. If particles coarser than 1 millimeter is there, there are every chances of clogging that hole because of the overlapping of the particles. Even suppose if the particles are smaller than 600 micron, again because of adhesion of the particles, there may be sticking of the particle with each other and hence clog the hole. To avoid that clogging of the hole, it may be because of the oversized particle or because of the undersized particles. For the free flow movement, for the free movement of sand, we use the sand passing 1 millimeter sieve to 600 micron or 300 micron. So, if you use sand passing 1 millimeter and range between 1 millimeter and 600 micron or 300 micron, it is a uniformly sized particles. That is what we use this uniform sized sand particle for easy flow. So, once we calculate the density of the sand in the laboratory, then we can go to field along with the sand. So, before going to field, again replace the sand poured already on the glass plate to the sand pouring cylinder and replace also the sand poured into the calibration container into the sand pouring cylinder. Again, note down the weight of the cylinder plus sand, that is W4 grams before going to the field. Take this sand with a tray with a central hole into the field and also take the suitable soil remover to make the hole that in the field. After visiting to the field or going to the field, in the field you have to prepare the level platform by clearing the roots or shrubs if at all if there is any, or these pebbles if there is any, and by using the tray mark the central hole. After marking the central hole, you have to remove the soil approximately to a diameter of 10 millimeter and to a height of 15 centimeter. Carefully make the hole and collect the soil removed from the hole separately. Collect the soil removed from the hole separately. Let it be W gram. Next, place this cylinder and sand exactly on the hole made in the field. After placing the cylinder and sand, open the shutter, permit sand to flow into the hole. Next, close the shutter. It will be like this. This is the hole made in the field, the ground surface. Place the cylinder over the hole and open the shutter. Close the shutter if there is no further movement. Then if there is no further movement of sand, then carefully lift the cylinder with remaining sand, and we can see this type of the arrangement. Sand will be poured into the cylinder, it forms the heap, even that heap extend above the ground surface. Next, come back to the laboratory. In the laboratory, note down the weight of cylinder plus remaining sand. After pouring into the hole, that is equal to W 5 grams. So W is the weight of the soil removed from the hole, capital W, and W5 is the weight of cylinder plus remaining sand after pouring into the hole. Now again, we need to calculate weight of sand required to fill the hole horizontally, like in the previous case, like in the case of calibration container. There we pour the sand into the calibration container, then we worked out the weight of the sand required to fill the calibration container horizontally. Similarly, here we need to find out weight of sand required to fill the hole horizontally. Next, weight of sand required to fill the hole horizontally is equal to, let us call designated as WS, that is equal to, use these two observations W5 and W4 along with this WC. So this heap is nothing but a conical weight of sand required to fill the conical portion. WS is equal to W, obviously W4 is greater than W5, W4 minus W5 minus WC. So we get weight of sand required to fill the hole horizontally. We know weight of sand required to fill the hole horizontally, and we already calculated density of sand. Gamma S is equal to WCC divided by VCC. Next, volume of the hole can be determined by using this density of sand and weight of sand. So we know that density of sand is equal to weight of sand divided by volume of sand, that is nothing but volume of hole. So we have gamma S is equal to weight of sand divided by volume of sand. Therefore, volume of sand is equal to weight of sand divided by gamma S, density of sand. So volume of sand is nothing but volume of hole. WS is equal to V, that is equal to volume of hole. Already we removed soil. We know the weight of soil removed from the hole. and we know volume of the hole. Knowing weight of the soil removed from the hole and volume of the hole, we can comfortably determine bulk density or field density. Gamma B is equal to W divided by V, gram per cc. So this can be achieved instantaneously both in the laboratory as well as in the field quickly within the fraction of hours, within say within 30 minutes or 1 hour. Next, take soil sample for water content determination from this W. Complete the formalities, say W1 weight of the empty container, W2 weight of the container plus wet soil, and keep that soil in the oven for drying. After 24 hours you will get W3. Using W1, W2, W3 we can determine water content. So water content W is equal to W2 minus W3 divided by W3 minus W1 multiplied by 100, that gives us the water content. Using this determined water content and already known field density, we can comfortably determine dye density. Gamma D is equal to gamma B divided by 1 plus W, so many gram per cc. Of course, this can be conveniently expressed in the form of kilonewton per meter cube in SI system by multiplying this by 9.81, so many kilonewton per meter cube. Generally we take the field density of as average of 2 or 3 determination for all important works. So by using this simple procedure, we can determine the density of soil in the field. When compared to previous method, this method is more accurate because here we use this method when we make the hole in the field. Below the surface we do not know what is there, whether there is a pebble or a gravel or a grass root, something like that. While making hole, usually we come across this type of irregular inside surface, and it is not so easy to determine the accurate volume of the hole made in the field. For that, if you use the sand will easily occupy the irregular surface in below the ground surface, and it gives accurate volume. So we can easily determine the field density by using this sand replacement method. And this method is can be used for all type of soil. It can be used in case of soft soil or clay soil. It can also be used in case of sandy soil, gravelly soil or boulder soil. Most commonly this method is used during the construction of embankment. During the course of the construction of embankment, it is necessary to check the compaction at regular interval after compacting each layer of the soil. So there, instead of disturbing the already compacted soil by using core cutter method, if you use this method, simply we disturb only that 10 centimeter diameter and 15 centimeter hole. Of course, and if you fill that hole by using this sand, it gives it won't disturb the soil, and in fact that sand gives very good strength to the embankment, and also it is very good drainage media. So likewise we can determine the field density of the soils. The next index property is the relative density. Relative density or density index, and it can be denoted as ID. As we have seen the limitation there in core cutter method, though it is possible to drive the core cutter into the sand, if you remove the core cutter, will get only core cutter back, we don't get soil. It cannot be accommodated. That is the biggest limitation. We come across all type of soil, coarse natural deposit, fine natural deposit, or well graded soil which represents all the particle sizes. Again, the denseness or looseness of the natural coarse deposits or coarse soil particle deposit can be expressed in terms of relative density or density index. Based on this relative density or density index, we can easily grade the soil, or we can easily classify the soil as a loose soil, a dense soil, or a medium dense soil, or a very dense soil, or very loose soil, like that. It is defined as the ratio of difference of void ratio in its loosest state and natural state to the difference in void ratio in its loosest state and densest state, and is expressed in terms of percentage. That is, relative density ID is equal to E maximum minus E, that divided by E maximum minus E minimum multiplied by 100. It is defined as the ratio of difference of void ratio in its loosest state and natural state to the difference of void ratio in its loosest state and densest state. Here E max represents void ratio in its loose state, E minimum represents void ratio in its the densest state, and E is the natural void ratio. Soil to be denser means voids should be minimum, and soils to be loose means voids to be the maximum. In natural state, soil will possess some void ratio. Based on this relative density and index, we can classify soil like this. The value of relative density then classification. If relative density is less than 15, then soil is said to be very loose. If the relative density ranges between 15 to 35, it is loose soil deposit. If it ranges between 35 to 65, it is called as medium soil or medium dense soil. If it ranges between 65 and 85, it is called as dense soil. If the relative density ranges between 85 to 100, then it is called as very dense deposit. Like this, so based on relative density, we can classify soil as loose, very loose, medium, dense, and very dense sand. Based on this value, knowing the relative density of the coarse-grained soil deposit, even it is possible to achieve correlation. We can correlate to other index properties and engineering property for all practical purposes. So, relative density, the term relative density is purely applicable to coarse soil deposit. In-situ density is nothing but it is applicable for all type of soil. Based on the type of soil which you come across in the field, we use the determination of in-situ density by using core cutter method or sand replacement method. Whereas relative density, the term relative density is purely applicable for coarse soil deposits in the field. So we can also come across some simple numerical problems that you can easily refer, and we will take it as assignment problems. We will give you those problems along with your the notes. So we'll with this we'll conclude the today's class. The next class will take up another index property, namely particle size distribution of soil. Thank you.